afternoon, everyone, depending on where you're joining us from. My name is Mark. I'm the product marketing manager here at Robotiq, and I'll be your moderator today. Just to make sure that the audience can hear us okay, if you can give us a little reaction button. So on the bottom left side of your screen, just to say if just a thumbs up. Perfect. Jory, Shug, Tatiana, thanks so much. Perfect. So we have half an hour together. That will go pretty quick. So let's just jump right into it. So the agenda for today, we'll have a speaker's introductions and a company and product overview. And then we'll have a moderated discussion on what does it actually take to deploy physical AI from a research, demo, and deployment perspective. And then we'll have an open Q&A. So the questions, you can answer them at the top right corner. There's an icon for the questions. Feel free to put them there, and then we'll be able to answer them at the end. So without further ado, Marianne, Vincent, and Jennifer, the floor is yours to introduce yourselves. Thank you.
Perfect. Hi. My name is Marian Körber. I'm a team lead for AI tools for Franka Robotics. My team is basically working on the intersection of AI research tooling and robotics, basically taking care that the work researchers are doing with our robots translate to real and reliable AI applications.
Hi guys, I'm Vincent. I'm a Robotiq co-founder. We founded about 18 years ago now. I am currently CTO AI at Robotiq, but also I'm a university professor at École de Technologie Supérieure in Montreal, with some emphasis in my research into sensor and AI, how we use those sensors. Thanks.
And hi, I'm Jen. I am an AI specialist at Robotiq. So I have a background in robotic manipulation using tactile sensors and data collection. And I am now working with Robotiq to help align their different sensors and grippers and end-of-arm tooling with this new wave of physical AI automation.
Sweet. Thank you so much for joining. And yeah, over to you, Marianne, for just an overview of Franka portfolio.
Okay, Franka Robotics is a research-driven robotics company based in Munich, Germany. And we are building what we believe is the reference platform for AI robotic research, combining robotic hardware, software stack, programming capabilities in actually one system. And our clients include the world leading teams regarding corporate and academic research, like NVIDIA, Meta, Google DeepMind, but also universities around the world, like Stanford, MIT, and a lot of others. So our main product is the FR3, the Franka Reachers 3, which we see here on the left side. It's force-sensitive 7-degree robotic system, and it is actually built to enable every researcher to do its research in the AI field. What you see here in the middle part, it's actually the next step that we developed. So it's basically two FR3s on one platform. We call it FR3 Duo. We optimize this configuration of both robotic arms in a way that you maximize the reachability of these robots. This enables you to actually interact with the physical world the same way as we humans are doing it. And adding to this, we have 3 cameras, 2 wrist cameras, and also 1 head camera in the middle. And of course, 2 robotic grippers attached to it. And the next evaluation is the mobile FR3 Duo. It's basically a holonomic mobile platform and a spine to move the FR3 up and down. And yeah, so this is Franka Robotics.
Thank you so much. And Jennifer, if you would be able to go through the Robotiq side.
Yeah, so Robotiq has been kind of one of the main players in the end-of-arm tooling for robotic arms for the past, as Vincent said, almost 2 decades. I think similar to Franka, we have been very prolific in research labs with huge companies. I think anyone familiar with robotics can see that the Franka and the robotic assets are kind of the tutorials and the kind of starting points for anyone looking to get started in robotics in terms of documentation online. And yeah, so our range of products are these end-of-arm tooling. So our grippers, particularly our flagship 2-fingered under-actuated gripper, which allows you 2 degrees of freedom with only 1 actuator. This is a gripper that is deployed in over kind of 25,000 different units. It has different features, like you can control the position, the speed, the force. It has an inbuilt mechanical compliance that makes it very useful for if you run into things, you don't have to worry about your finger snapping off. We also have our handy grippers, which are a more classical parallel gripper with a high IP rating. So it's good for all of those dull, dirty, and dangerous environments that you want to actually automate. We have our force torque sensor that can be mounted to the wrist of collaborative robot arms. And then we've also just recently released our first sensor directly for the physical AI market, which is our tactile sensor fingertips that are compatible with our 2F adaptive grippers. So with this, you can get that sense of what is actually happening in the hand during your manipulation tasks that we're looking to see how that enables the kind of betterment of these physical AI models in the real world.
So thanks so much, Jen. So I got a couple questions for our speakers today, just to get the conversation going on what does it take to actually deploy physical AI, not only in research, demo, and deployment. So my first question would be to Marianne and about for Franka. So what hardware properties a research lab now needs in the context of physical AI, and what would you tell a team that's choosing their platform today?
So yeah, I would say robotics, the topic robotics is changing a lot nowadays. In earlier days, it was like you had an end effector and a robot attached to it. And the only goal of the robot was actually to guide this end effector to a specific pose or to reach a trajectory regarding accuracy and reliability as well, and doing it all over again and again and again. And I would say these requirements are still valid, but there are more requirements nowadays. And that's the big point of also Franka Robotics now, because the embodiment plays a huge role, specifically regarding compliance, dexterity, and also a fast control loop. Like our robots, for example, have a 1 kilohertz control loop. So this actually gives you a rich idea on what's happening in the world, the environment the robot is acting in, and also and also the inside, what's actually happening inside of the robot. And this is the thing. This is the big point. This richness, the joint talk information, and also the action space and the observation space. This is actually what's the big values of these robots nowadays. And we are not just collecting camera frames after each other, because what we are collecting is a full physical interaction. And this is a huge difference to the earlier days. And so for now, it's actually important of what the robot does physically, like how it complies, how it reacts to contacts, how it moves. And all of this data, all of this information is encoded into the training data. And so, yeah, this is the challenge nowadays. And the embodiment basically determines the quality of the data. And in the world of AI, the quality of data is what counts. And that's why what we develop in our system or in our ecosystem is like one standardized embodiment, but also standardized toolings. For example, data collection pipeline, training pipeline. This enables researchers around the world to, for example, generate training data in Munich and train a robotic system in Tokyo, because everything is standardized. The robotic labs nowadays are not isolated anymore. They can share training data, they can share models, and their research results, and use it around the world.
Yeah, I feel like the data quality and the hardware are very much intertwined. So that brings really also the gripper at the center of the picture. So I guess my next question would be for Jennifer or Vincent. Why multimodal data and gripper choice sets the foundation for physical AI?
Yeah, I'll go. I think it's just building off a few of the points that Marianne just said, is that we are entering this phase of how these physical AI models learn and are optimized is the quality of the feedback around the physical interaction. The more understanding that the model has of the physics of how something is being pushed into the gripper, how something is slipping through the palm, that will allow the models to actually react better and adapt better to the real world changing environment. And most of those interactions happen at the end of ARM tooling, right? It is the gripper that is doing the majority of the physical interactions with the objects within the task or whatever. So ensuring that you have a piece of hardware that can, one, get the information that you need, whether it's the force, whether a certain level of mechanical compliance, whether it's being able to control the speed or position of your gripper. These are all tools that your physical AI model will be able to leverage to better interact with the world. And again, different sensors, so tactile sensing, allowing you to react to different contact patterns in different ways, just allows you to build a stronger foundation for your physical AI model. And one of the other kind of important aspects is you have the quality of the data, and then you also have this scale of data that if you want to be training these models, you're going to need, the numbers floating around are billions and trillions of data points. And so you want hardware that is actually going to last as long as possible and give you consistent feedback through that time. So like our grippers are warranted for 2 to 5 million cycles. And if you think about training models and collecting data on the scale of millions and billions, yeah, having hardware that can actually last for that long is super important. And I think we did 2 million cycles on our tactile sensors as well, and it's still going, still working. So yeah, these choices that you make at the beginning and knowing that, oh, these hardware choices are going to last for all of my data collection cycles and then maybe my deployment cycles, have a huge impact on how well your systems will scale and deploy.
Yeah, I think that sounds very much really aligned with what we can see in a demo as well. So I think if I'm just going to play some videos here, and I'll try my best. I'll see if they are working okay. I think it's just a little bit too much of a delay here. So just as a disclaimer, I'll share the video, and then there will be a bit of sound. So just be ready for it. And I'll try to mute on my side, but let's see. So that was just to show like a video here. So what we just saw was like a generalist policy reacting in real time. So no waypoints or no script. So Marianne, just to kick off the conversation more on the demo side, can you walk us through what actually is happening at the robot side, and more importantly, what does tend to break first?
I mean, yeah, perfect. Thanks. This is a demo that we did together with Gemini Robotics. We have these other videos as well. On the left side, you actually see a tape being handed over from one hand to another and then put into the box. On the right side, you see actually a bottle being gripped, put onto the table. So this is all based on a model, on a generalist model. So we didn't fine tune this model. It's a Gemini Robotics on device model. And basically what we see, as you said, there's no script, there's no waypoint, there's actually no plan, no trajectory to be done. Basically, the model is making decisions based on the visual input and based on the robot state that it's getting. Yeah, so there's no fixed plan. And here's the point. I mean, the model works well, but the big question is, can the embodiment actually keep up? Can the embodiment like keep up with the commands that the AI is giving it? And here's where a lot of applications break. So you need to have very robust hardware. You need to have hardware which is giving the model enough information to be able to decide on what it has to do. Because the only thing, as I said, it's basically we are telling the model what to do. There's a prompt you are inputting with a microphone, just telling what it should do. For example, pick up the lamp and put it into the green box, and it's doing it. But if your embodiment is not able to give you enough information about the environment and about the robot state itself, then it doesn't work. So this is where Franka robots and Robotiq and effectors actually work well together, because they are reliable and they give us enough information about this environment. And that's why we are actually looking into this combination a lot and doing actually all of our demos and applications with Robotiq grippers.
Vincent, I would be curious to hear you about that part of the process too. So how do gripping, touch, vision, how they work together to turn what the model perceives, what it sees, and to something that robot can actually execute?
That's a pretty open question, but my take on this is that although they work together, they also work in sequence. They have all each very important part have their own role in completing a task. And I was not surprised when we started to see VLA everywhere. We're not surprised because vision and language is kind of a very good pairing. Is the starting of a robot task is more like, hey, go grab that yellow mug. So that's understanding of the language of what I want to achieve. And then you have the vision system and the algorithm, and the LLM are pretty good into this. So, hey, here is the yellow mug and you grab it. So that's more to me like the intention. Then vision also is used during how we go to that task and then arrive the point where it's become about doing the task and is the gripper, is the end effector. And well, I think Jennifer mentioned about like the robustness in, we've seen it in digital application. It's tough for the gripper because it's where contact happen, contact with the object, but also unwanted contact with the environment, the table, the things like that. But yeah, that's to me, the touch and the vision interaction. But I think, and that's why we decided to commercialize tactile sensor platform. We made it probably 15 years ago in the market, like people that weren't ready for that. But I think touch is one very important part where vision kind of fail. I mean, vision is very important. It's not one against the other. It's very important for the first phase up to the contact. But when you arrive in contact with object, it becomes more about force, pressure, contact. And that's the difference. I mean, if you ever try to accomplish some task with glove on it, it's way harder than with our bare hand. And the main difference is our ability to feel touch. So one of the hard point is there's no standard when it comes to touch. And It's not like vision where we have a good understanding of like what is an HD image or something like that. But one of good inspiration we had was human. We know human is very good at dexterity, so we kind of try to mimic this. So our sensor is multimodal. It's a pressure image that gives you a good idea of what is the contact that happened, but there's also vibration that can detect micro slippage, recognize texture, and things like that. But also there's an IMU that give you the configuration of the gripper, like since it's under-actuated and even though you would know the motor position, you don't know the exact configuration of the fingertip. And all those modality can be used to enrich data set for the point where you start to interact with the object. And I think it becomes even more important when you try to not only do pick and place tasks, but also task in constraint and motion. So that's my take on it.
Yeah, so and you touch base also on reliability. I think it's a good segue for the next section here on actually deploying hardware in physical AI and in a real production floor and in an industrial way. So I guess my question for either Vincent or Jennifer is, from your experience working with manufacturers and integrators, why does hardware play such a big part on the production floor? And what actually breaks under real operational pressure that didn't break in the lab?
Maybe I will take this question because I have a historical perspective on it. When we started robotics 18 years ago, I was not aware. I had the vision of, yeah, we'll go sell this three-finger gripper. We didn't show it here. And that it's going to be like people will adopt it in the industrial world. And first meeting, we had a spring on the gripper, and first meeting, people started to ask, saying, spring will not survive industrial application. So, and that teach me a lesson of how hard it is in real industrial application, and how people are reluctant to have anything that could go down even for an hour, because an hour of down production is pretty expensive. So we have been in this business for years, and we've improved our product, and it's very important to have very reliable product in that world, but also because shit happens sometimes. If something breaks, to be really fast at replacing it and keep the production going. So that's the world where we come from. And I think on the data side, it is important again. And I think, and that's the data flywheel you have here at Marc-Antoine, is it's very important because you want consistent data when like you do the cycle. And in my lab, I said a university professor in my lab, we did teach we did a lot of data collection, and sometime with some hardware, he realized that after 10,000 of cycle, the data, the output, it's not the same. Like in our gripper, you have the current of the actuator, and that's related to the force. But if that relation change after 10,000 cycle, 20,000 cycle, 30,000, it become very hard to use the data. So a very reliable hardware is very important for the data collection, because it's important to the training. But also then if you want to use your training and go into the real application, and I think that's the thing that's presented here, is that flywheel, is that you can then deploy on a hardware that can survive in an industrial environment.
Thanks so much, and I think it's a good segue as well for the next one. More of an open question for all of you. What would be, in your opinion, at least, what would be the most underestimated cost in physical AI deployment? Something that we didn't discuss today.
Shall I take it?
Yeah, for sure, please.
Cool. So on my point of view, it's definitely the data collection. This is still a question where we don't know where the development of foundation models or robotic AI applications will go to. I mean, we had 40 years where people were feeding the internet with information, and this was the base data that was used to train the big LLM models like ChatGPT, Claude, and so on. But for the robotic data, all the companies were very careful in giving out data. It was not collected, and if it was collected, not in the right format or in any case. So we have to start up all over again. And for now, we don't know what's the best way to approach it. So we need to collect those data as high quality as possible, context-rich data as well, with those fingertips, like information about how hard I'm gripping and where I do have which forces, and this will cost a lot of time to generate those data that we don't have for these models.
Yeah, I would 100% agree. It's so much effort to get data from real robots. And I think along these lines too, is that because we don't know necessarily exactly what we need, everyone is collecting every data at as high quality and as high streaming as possible. And so I think a lot of companies are going to eventually hit this just these huge, massive data sets that they're then going to have to try to trim down and search through and figure out, oh, like, how actually do I train my models on specific tasks to optimize for a certain like reliability that I need to actually deploy this robot, to like sift through maybe because one of the idioms in machine learning is garbage in, garbage out, and ensuring that the data that you put in is high quality when we're in this, I think as roboticists, we feel behind. We're like, oh my God, there's not enough data to have these models. So we're just going to collect everything. And that bill is going to come at some point down the line for some of these companies going, oh, what actually did I need? And going back and sorting through. So it's, yeah, I think there's going to be some bills to pay at some point for some companies for sure.
Vincent, do you have a take on it before we move to the Q&A session?
If there's an underestimated cost, I think also it's time. It's people don't realize, and I think it has been said, but also linked to something Marianne said at the beginning is as like more your setup is easy to deploy and use, it will save you time because it's pretty time intensive to collect data, and we hear like people get from 5 to 8 hours of telemanipulation, 2 hours of good data. So it's really time. And I think Marianne mentioned it is in the internet world, we're used to like a data set with 4 million of image, and it's kind of number we're using the LLM, but also before like the deep learning has been based on that amount of information, and it's not the case. I mean, collecting 100,000 of data on a robot is pretty a long process. And it's pretty data extensive. So yeah, I think it's all the time it takes. That's probably the underestimated cost.
So thank you so much for that. We have one question here in the thread, and it's from Eden. So he's asking, robotics is moving from control problem into a data and operations problem. Do you think the current software tooling, like DevOps, is sufficient for the ops in robotics?
I think this, well, I was just going to say, I think this is, my view is that everyone's kind of making their own custom tooling. So I think to answer that question is that no, the current software tooling is not sufficient. Everyone is building up their own tools. And probably at some point it'll converge into a few things, but from what I've seen, no, everyone is making their own custom thing to handle these data operation problems.
And this is basically the problem, I would say, nowadays. With different tools, you also have different training data sets. So you can't you can't just use the whole set of training data set which is out there, because you need to adapt specific training sets. You need to change formats to get it into your format that you need for training. So that's why it is so important what we are building, to having this reference platform with a standardized setup. This means like embodiment. Let's call it like this. It means Franka robots, Robotiq grippers together, and to generate data with the same tooling, and to be able that researchers can generate training data, publish it, and train their models on a huge training data sets, which actually fits to this embodiment, or fits to the way this model is trained for. And that's why, I mean, we are trying to get this ecosystem up in place. We will see how the community is reacting to it, but we definitely hope that it will have an impact for robotics and AI.
If I can also add my thanks on one specific part of the question. So the question was saying that we go from a control problem to a data one. Is that the exact, Marc-Antoine, can you repeat that?
Yeah, the first part of the question was robotics is moving from control problem into a data and operations problem.
So actually it's true, and people are collecting data and try to solve like a hand-to-hand approach. And if you look at the VLA, at the end, right now, like in the 100 of demo that I have seen, is most of the time is the action that don't perform as well. And I think it's where, like, if you have a hand-to-hand approach, you need a lot of data to rely on. But I also see very great demo where the action part was incredibly efficient. And most of those demo, they had the data to understand the task, the application, but the action was still very deterministic with a very control engineering approach. Like at the end, we do know kinematics, we do know the equation, so do we have to learn it? I mean, it's an open question, but at that moment, I think we might see a movement back to an hybrid data and control approach.
Sweet, thank you so much. I think that's well, that's all the time that we have today. Thank you so much for the insights, Marianne, Vincent, and Jennifer. Thanks so much for joining, and everyone in the audience. Thank you for participating here in this webinar. The recording will be sent to you, so you can refer to it anytime. And as you see here on the screen, there will be, you can talk to an expert today. We'll be happy to help you in all the aspect of your project. So reach out to us, please, and we will see you next time. Thank you so much for joining, and you have a good day. Thank you so much.
Thanks, everyone.
Thank you.
Bye. Thank you for your time.